You're listening to Conferences on Lyme Allergy from Children's Mercy Hospitals and Clinics in Kansas City, Missouri. Today is January 31st, 2011, and I'm your host, Dr. Jay Portnoy. Our topic today, Abbas Chapter 14, Humoral Immunity. Our presenter is Dr. Christina Ciaccio. She's in the section of Allergy, Asthma, and Immunology at Children's Mercy Hospitals and Clinics. Our first presentation this morning is a continuation of our ongoing series on immunology, covering the Abbas book on immunology, and this is Chapter 14, which deals with humoral immunity. And our presenter, as usual, is Dr. Christina Ciaccio, who's an assistant professor here at the University of Missouri Kansas City School of Medicine and also a faculty member at Children's Mercy Hospitals and Clinics in the section of Allergy Immunology. So without any further delay, I'll go ahead and turn the podium, or the keyboard, I suppose, over to Dr. Christina Ciaccio. Take it away, Dr. Ciaccio. I think I just disconnected something. Mouse. Or you can use the wireless mouse if you prefer.
All right. Do you have something in here?
Oh, just go to the window.
Oh, okay.
There you go.
All right. So this was going to be 2 lectures, and it's now condensed into one because of our snow day earlier. Let's see what we can get through. Okay, so today we're talking about the effector mechanisms of humoral immunity. So we're going to be talking a lot about antibodies and complements. So, first, a word about antibodies. The function of antibodies is neutralization and elimination of microbes and toxins. They're produced by B cells and plasma cells and lymphoid organs and bone marrow, but they perform effector functions at sites distant to their production. They can be derived from short-lived or long-lived plasma cells following activation of naive or memory B cells. Their function is mediated by the heavy chain constant region. The different heavy chain isotopes serve distinct functions. Functions are triggered by binding of the antigen to the variable region. It's all pretty straightforward stuff I think we know by now. All right, so our first picture today is figure 14.1 on page 322 of Abbas. And it shows the effector function of antibodies. So, of course, you have your B cell is generating antibodies after exposure to a microbe, which can then neutralize the microbe and toxin, and they can opsonize for phagocytosis. They can mediate antibody-dependent cellular cytotoxicity, and then via the complement activation, they can cause lysis of microbes, phagocytosis, and inflammation. Table 14.1 on page 323 shows the functions of the different antibody isotypes. So IgG in particular is helpful in opsonization, activation of the classical pathway of complement, antibody-dependent cell-mediated cytotoxicity mediated by natural killer cells, neonatal immunity, and then feedback inhibition of B-cell activation. IgM is great at activation of the classical pathway of complement and is used as an antigen receptor for naive B cells. IgA is primarily used in mucosal immunity. It's secreted into the lumen of the GI tract and the respiratory tract. IgE, of course, is helpful in mast cell degranulation. And IgD, we really don't know. So neutralization. So antibodies block binding of microbes and toxins to cellular receptors. They prevent infection by this mechanism by steric hindrance. In the blood, the main neutralizing antibody, like we just talked about, is IgG. In the mucosa, the main neutralizing antibody is IgA. Figure 14.2 again shows neutralization of microbes and toxins by antibody. So without antibody, the microbes have access to epithelial cells and cell receptors, but they're blocked by steric hindrance if they are coated with various antibodies. Opsonization and phagocytosis. So IgG coats microbes and promotes phagocytosis by binding the Fc receptors on phagocytes, and this process is called opsonization. These Fc receptors promote phagocytosis of the opsonized particles. They deliver signals that simulate the microbicidal activities of the leukocytes. So, as we've talked about before, all receptors on cells are labeled, R. So when we're binding an antibody, we call it an Fc receptor, and then we use the Greek letter gamma because it binds IgG. And then we know of 3 Fc gamma receptors, or FCR, FCR1, FCR2, and FCR3. They are also known as CD16, 32, and 64.
Powers of 2.
Powers of 2. Here, I didn't, since this chapter is so long, get into much in the green boxes, although I think they're worth looking at. And this goes over the different Fc receptors. I think it's important to remember that the middle one, Fc gamma R2B, is an inhibitory. It has an ITIM instead of an ITAM. And remember, CD64 Fc epsilon R1 is the high affinity IgG receptor. Talks a little bit about the subunit component, subunit composition of the Fc receptors. It's on page 327 of Abbas if you'd like to take a look at it.
So 64 is the highest affinity, then 32, and 16 is the lowest affinity. Is that how?
16 is the lowest affinity. Fc gamma R2 is not high affinity either. It's low affinity, but it's also inhibitory. But yeah, it's sort of reverse order if you're thinking of affinity.
What does it inhibit?
Feedback inhibition of B cells.
So when B cells bind by the FCR2 or CD32, it actually decreases their activity?
Correct.
Why would you want that? That would be like an autoimmunity or something? Or?
No, but you want, if you're getting overwhelmed, you want a mechanism to stop infection once the infection is getting cleared.
So if all of the 64s are used up, then the 32s are left, and then they start to turn down the reaction. It's like a thermostat kind of thing. I didn't realize that before. I guess it makes sense. The 64s would get used up first because they have the high affinity. So once they've done their job, then the B cell is kind of overloaded, and then the 32s are left. They wouldn't have gotten used up early because they don't have a lower affinity.
I think 32's IgG may be free. I'm not sure about.
That's something. That's how the IVIG is thought may help in autoimmunity. So
IVIG, because it uses up all the 64s?
Well, it didn't say that. It just mentioned that inhibitory component that may be, didn't say it was, but it just said it may be how giving IVIG can down-regulate like that.
Well, because for a long time, the IVIG, there was a question of, well, is it the antibody specificity of all the different antibodies of IVIG, or is it the FC overload that, because you're just giving them this massive dose of FC antibodies containing FC receptors, or FC components. And it seemed that it wasn't the specificity of the antibody. It's not like the antibody goes in and it neutralizes everything that comes in, especially for autoimmunity. What is it neutralizing? That wouldn't make any sense. And so how could it decrease an autoimmune reaction? And it may be that by giving this massive load of IgG, and you really need to get grams of this stuff, grams per kilogram, you're using up all the CD64s, and therefore you're starting to stimulate the 32s, which start to decrease the immune response. So that may be the mechanism. So that's right.
All right. So figure 14.3 on page 325 of Abbas shows antibody-mediated opsonization and phagocytosis of microbes. So here's your microbe, and IgG is coding it. IgG, the Fc part, binds to the Fc receptor, Fc gamma R1. And this binding does two things. It causes this microbe to be phagocytosed, and signaling through this receptor also upregulates the reactive oxygen species inside that will then kill the microbe once it's ingested.
Here's a question. Does the IgG, you've got all these IgG antibodies here, but they're not bound to these FcR1s yet. When it binds to its antigen, does that change the Fc receptor so that it becomes more bindable to the Fc receptor 1?
Oh, that's exactly actually just what I was looking for. You know, I was wondering if to bind to it, it has to be
bound.
Something about it has to be bound to the microbe, whereas if it's binding to Fc gamma R2, it doesn't. It can just be free.
So free IgG can bind to the FcR2. But FcR1, native IgG can't bind to FcR1 unless it's itself bound to a microbe.
Oh, that's something it's antibody conformation changes.
Yeah,
It's like they call it an allosteric change in the structure of the Fc receptor.
They mentioned that somewhere.
And the Fc receptor actually changes its configuration when it binds to this antigen, allowing it to then bind to the Fc receptor 1. Otherwise, you have a lot of IgG antibody floating around in the serum. You'd think all these receptors would be filled up with IgG antibodies, but they're not. So obviously, just plain unbound IgG isn't going to bind to those receptors.
I think I remember saying like there's a 3D conformational change once the antigen's in the site that makes the receptor available for the binding.
Right.
Or makes the
I think
antibody
that's an
available.
important thing to note.
FcR1 is used for phagocytosis mostly, so
Right. But if the IgG is not bound, it's not going to phagocytose anything.
right.
You're just going to fill it all up.
Yeah, I can't find R2B. I think R2B didn't need to be bound, but maybe wrong.
Interesting.
Okay, so just a word about antibody-dependent cell-mediated cytotoxicity. So NK cells bind to antibody-coated cells, also by Fc receptors, and by this mechanism, the NK cell destroys the opsonized cell. This utilizes Fc gamma R3.
Right. That's the CD16,
16.
and that's on NK cells.
That's on NK cells. Actually use it as a marker for NK cells.
It's one of the markers for NK cells along with CD56, isn't it?
Mm-hmm.
So if you have those two, then you've got an NK.
So here we have ADCC in a picture form. It's figure 14.4 on page 329 of Abbas. We have our surface antigen on our infected cell. IgG is binding to it, and then IgG binds these low affinity gamma receptors. And then the NK cell mediates death of the infected cell, the target cell.
Is that a microbe or a cell?
It's a cell.
So as opposed to a bacteria, it might be a larger object that an NK cell would attack, or
Well, it's actually an infected cell, yes. Or I guess,
virus-infected cell, perhaps?
yeah, if it's displaying surface antigen. I don't know if it has to be cell. So IgE, so antibody and mast cells, eosinophils, work together to mediate expulsion and killing of helminthic parasites. So in general, these helminthic parasites are resistant to phagocytosis because they're large and they're thick-skinned. So the skin they have is resistant to the reactive oxygen species inside the phagocytes. However, they can be killed by the major basic protein in eosinophils, that we touched on last week a little bit. And of course, the preformed mediators in mast cells that are released during degranulation when the Fc epsilon R1 receptor is activated. Of course, here we have an Fc receptor, R for receptor, it's binding Fc, and then epsilon for IgE. So it's binding IgE. We put 1 is the nomenclature for high affinity IgE receptor and IgG receptor. Yep.
So I kind of think of the eosinophils as the neutrophils for helminths, because the neutrophil doesn't really do a very good job of phagocytosing and killing helminths because it just doesn't have the right stuff. It's great for bacteria and I suppose virus-infected cells, but helminths are different, so you need a different thing to kill those. So that's what the eosinophils do, and you don't want them to bind with IgG also. How do they know that a helminth is different than a bacteria or a virus-infected normal cell? And so this is a way of alerting it. So you make IgE against that, and then it's basically the neutrophil of the helminths. It's interesting. It's good to think of it that way because it helps to keep it all in mind.
All right. So on to the complement system. This is the major effector mechanisms of humoral immunity. It consists of serum and cell surface proteins that interact to eliminate microbes. Activation of the complement system involves sequential proteolysis of proteins to generate proteolytic enzyme complexes. So the products covalently attach to the microbial surface or antibody on a microbial surface. They are inhibited by regulatory proteins on normal host cells, which are typically absent on microbes. This can be initiated by 3 pathways, the classical, alternative, and lectin, all 3 of which we're going to go through.
So it's not like the complement knows not to bind to non-bacterial cells. It's just that when it does bind to those, it gets inhibited.
Yeah. Okay. So it doesn't matter which pathway started, but the generation of the MET complex is dependent on the formation of 2 things, C3 convertase, which of course cleaves C3, and C5 convertase, which cleaves C5. No matter which pathway you're going down, the formation of these 2 things is essential. Figure 14.5 on page 331 shows all 3 pathways, alternative, classical, and lectin. The alternative pathway, they're all very similar. Of course, they make C5 convertase and their own version of C3 convertase. The alternative pathway spontaneously starts, classical, of course, starts with binding to antibody, in particular IgG and IgM. And then, of course, the lectin pathway is initiated by mannose binding lectin and then these masts, which are binding to mannose. Okay, so the alternative pathway. So the alternative pathway involves spontaneous cleavage of C3 to C3A and C3B. I have not included the anaphylatoxin the A's in this talk at all, but you may want to just keep in mind that they are used for chemotaxis and inflammation, and do a bit of reading on your own about those. C3b then attaches to the target cell surface. Factor B binds to C3b, and then factor D cleaves factor B, which gives you the complex C3b-BB, which is the alternative pathway C3 convertase. So remember, each pathway you want 2 things, the C3 convertase and the C5 convertase. So very easy for alternative pathway. Spontaneous cleavage, and then factor B gets cleaved by factor D, and you get C3b-BB. All right. So something called propyridin stabilizes C3b/BB. Propyridin is the only known positive regulator of complement. So at the end, we're going to talk about some negative regulators of complement, but these are the only positive regulators of complement.
That sounds like a board question.
And it's the only known excellent complement deficiency.
Yes.
It's an excellent complement. Wow.
Attachment propyridin is favored on microbes and not on host cells. So a second C3b, so remember we have the C3 convertase now already made, the C3b/BB. So the purpose of C3b/BB is to now start lysing more C3. So the first one was spontaneous, but now you're getting more C3As and C3Bs generated now that that convertase is made. So now a second one of these C3Bs will bind to C3b/BB to get C3b/BB, and that is the alternative pathway C5 convertase. The rest of those C3Bs that are generated by the C3 convertase are going to go on, and they can start their own pore or MAC complex.
This reminds me of linear algebra and matrix multiplication.
All right, so one more time. Spontaneous cleavage of C3. We're not going to talk about C3A, but the resultant big part of cleavage is C3B. So if nothing happens, if it doesn't find a microbe to bind to, it's very quickly inactivated. But if it binds to microbial surface, then factor B binds to it, factor D cleaves factor B, and then you get C3b/BB, which is the C3 convertase. So now this is going to start converting all kinds of C3s to C3Bs. One of these comes back and binds to the C3 convertase to become C5 convertase. C3 convertase,
that figure's a
C5
little
with C3.
misleading because the next figure shows the C5 convertase has the C5b part of it, not regular C5.
Are you talking about the classical complement pathway?
Yeah, no, that last thing. Or is that shouldn't that be C5b?
Oh, well, I think what it's trying to show is that C5 binds to it to make C5b. So C5, the purpose of C5 convertase is that it is converting C5 to C5b.
That's not part of the conversion.
Generation of C5.
Yeah, because C5 convertase is C5b.
C5 convertase does not have C5 on it. C5 convertase is C3b times 2 in BB.
Oh.
C5 is a substrate.
Oh,
C5 is
yeah.
the substrate that the C5 convertase is active. Just as C3 convertase does have C3 in it, but it's called C3 convertase because it's converting C3s to C3Bs.
Yeah.
C5 convertase is converting C5 to C5Bs.
Yeah,
Okay?
So C5 convertase is 2 C3Bs with that extra BB component.
yeah. Yeah.
So essentially it's C3 convertase to extra C3B.
Yeah.
Exactly.
Yeah.
For the alternative pathway.
Looks like Brock has
Yeah, that's right.
comments.
It's that, right?
Go ahead, Brock. You wanted to say something?
Yeah. I was just curious, anyone knows if these proteases are cysteine or aspartic or serine proteases?
Aren't they serine proteases?
Yeah, the relevance is that a lot of allergens are proteases. And therefore can get involved in this stuff, and it might be a connection why they cause so much inflammation.
Do you think there could be spontaneous complement activation by allergens?
The serine.
Certainly.
That's something we haven't really, hasn't been described, but it might be very interesting that you're right. It could be something that augments inflammation.
Right.
The box it says serine proteases or anything.
Serine.
Are they all serine proteases?
It says factor B, factor D.
I believe so, because even C1Q and C1R and C1S are serine proteases.
Okay. Okay.
So can you inhibit a serine protease with anything specific?
Sure.
C1
Sure. Alpha-1 antitrypsin.
which may be why alpha-1 antitrypsin causes so much damage, because you're getting activated of this pathway and it's not being inhibited.
Well, no, you're inactivating with these. A lot of allergens are also protease inhibitors. So there's something goes on locally, such as a protease, DRP1 or something like that. If it's local, then it can really cause a lot of inflammation, change the macrophages secretions, and induce IgE. So it's so the proteases work that way, and the protease inhibitors actually impact the same system. But we're not quite sure how all that works.
Wow. Okay. Very interesting.
All right. So we're going to stop here. For each pathway, I'm going to stop at C5 convertase, and then we're going to do the MET complex at the end. Okay. This is table 14.3 on page 332 of Abbas. So Abbas has some very nice tables for the complement, and this is the proteins involved in the alternative pathway of complement. Basically talks about the structure, the normal serum concentration, and the function, which we're not going to go over again. But these tables may be a good thing to copy and take a look at later on.
C3 is a heterodimer.
Okay, classical pathway. So the classical pathway, of course, is initiated by antibody. It's initiated by binding of C1 to the CH2 component of IgG or the CH3 component of IgM. C1 is made of C1q, which is a hexamer which binds to the antibody, and then C1r and C1s, both of which are dimers that are proteases. C1r activates C1s, and C1s cleaves C4. So the C1q is going to bind to the antibody, IgG or IgM. So remember, IgM has the highest affinity, and then IgG3, and then IgG1.
Oh.
The C1q binds to the antibody, C1r activates C1s, and then C1s cleaves C4. All right, so here's what it looks like. You have your C1q, and then your dimers of S and R are here. C1q binds to the antibody. It has to be bound, and C1q has to be bound in at least 2 spots for this to get activated. Okay, in the classical pathway, C4 is homologous to C3. C2 binds to the C4b. Remember, so QRS. So remember, C1s cleaves C4 to C4b. Now C2 binds to that C4b. And then C2 is cleaved by C1s to make C4b, C2b, which is the classical pathway C3 convertase. So remember, this job of this product is going to be converting C3s to C3bs. So some of those C3bs can go off by the alternative pathway and create their own MET complexes. So the alternative pathway can actually amplify this process. But at least one of those C3bs that's generated by the C3 convertase is going to latch onto it and then become the classical pathway C5 convertase. So C4b, C2b, C3b.
Mm-hmm.
Here we go. So here we have your C1 binding to the antibody. Remember, the C1 cleaves C4. The C4 is going to bind to C2, which the C1 also cleaves. And you have your C3 convertase. C3 convertase is going to cleave C3, which is going to come back and join onto it, and you have your C5 convertase. Clear as mud?
So instead of C3b, BB, C3b, you have C4b, 2b, C3b. But they both do the same thing in the end.
Yes.
So the pathways merge into one.
Yeah.
Exactly. So once you have your C5 convertase, all this work is to just make the C5 convertase and start converting C5, one way or the other. All right, so this is included, figure 1410 on page 336, and it shows, it is a reminder that the antibody must be bound to the microbe in order for the complement cascade to happen. So complement activation cannot occur with the soluble form of the immunoglobulins. All right. So just as in the alternative pathway table, there is a classical pathway table. It's table 14.4 on page 335. It goes over C1, which is made up of C1Q, C1R, C1S, the C4, C2, and then, of course, C3. Just talks about the function of each one of those. All right. Lectin pathway. The lectin pathway is our third pathway that can initiate the complement system. It's initiated by binding of microbial polysaccharides to lectins. And the example we hear a lot is mannose to mannose binding lectin. They also gave an example of N-acetylglucosamine to cyclins. So the lectins are homologous to C1Q. And then the mannose binding lectin binds to something called MASPs, which are MBL-associated serine proteases, and the MASPs are homologous to C1R and C1S. So MBL and MASPs are essentially C1. So it doesn't have a separate picture. So this is, again, figure 14.5 on page 331 of Abbas. You have your mannose, you have your mannose binding lectin, which looks a lot like C1Q. You have your MASPs, which are like C1R and C1S, are going to cleave C4, and you're going to get C4B, and then C2 is going to connect on, and again, this complex is going to cleave C2, and you're going to have C4B, 2B, which is your lectin pathway C3 convertase, which is exactly the same as your classical pathway convertase. It's going to convert C3. One of them is going to come around, latch on, and you're going to have a C5 convertase.
So the lectin is very similar to the classical pathway, except at the initiation step.
Yes, very similar. All right.
Yeah, mannose is a common component of many microbes, bacteria, like the carbohydrate cell walls, for example. They would have a lot of mannose, which human cells tend not to have.
All right, so what happens once we have C5b generated? Oh, wait, this is sort of in the wrong spot. Maybe I can mention it here. Okay, there is one variant that they mentioned twice in the book. There is a C-type lectin called SINE-R1. It's found in splenic marginal zone macrophages. It recognizes pneumococcal polysaccharides. It also binds C1Q and activates the classical pathway to help try and kill the pneumococcal polysaccharides. So it is one reason why if you're asplenic, you have trouble with encapsulated bacteria because of this receptor SINE-R1. Complement, by the way, I should have said this at the beginning, is a very testable area because the questions are so concrete. You can write a very easily worded question that there's no debate about the answer. So the pathways and the deficiencies, I think, are heavily tested.
Yeah, plus it's easy to say the answer is either C4A or C4B. And subtle differences in the little subscript can be used for testing, even though it's kind of trivia. So you ought to do really well on that.
Okay, so terminal complement. What happens after the C5 convertase is made? So the C5 convertase, like we talked about, cleaves C5. It initiates the late complement components. So C5b binds to C6 and C7. C5b, C6, C7 becomes the receptor for C8. And then the C8 is actually what inserts into the cell. C5b, C6, C7, C8 all together is going to insert into the cell with the help of C8. And then poly C9 is added. And I think this is anywhere from like 5 to 15 C9s can be added and forms a channel in the cell. And the channel in the cell allows movement of water and ions in and out of the cell. So once you have lots of these little pores in the cell is going to start to die. Table 14.5 on page 337 goes over all the proteins of late complement. But here we have it in picture form. So we have our C5 convertase. So this C5 convertase is from which pathway?
Alternate.
Great.
It's the alternative, yeah.
So it's converting the C5 to C5b, which is going to connect to C6, C7. C5b, C6, C7 is a receptor for C8. The C8 is going to stabilize in the plasma membrane. This whole complex is going to stabilize poly C9, which is going to form a channel and start cell life.
Well, what would the C5 convertase be for the alternative pathway?
C4b, C2b, C3b.
This is alternative pathway.
Oh, for the classical.
For the classic pathway.
Yeah. C4b, C2b, C3b.
Okay.
I think so.
Yeah.
4, 2,
4, 2, 3.
all the B's.
Yeah. 2,
Okay.
3, and 4.
B is appropriate.
Just got to get this straight, because that's a great board question. I can see which is the which of the 5 following is the C5 convertase for the alternative pathway, and list all these different things.
So this, of course, is called the MAC complex, your channel here. So this is a picture of a cell with lots of different MAC complexes on it. I guess this is one complete structural channel. All right. So I think the next two things are really heavily tested. Complement receptors and then the deficiencies, the regulators of complement.
So it does more than just create the MAC attack, doesn't it?
What?
Complement. It's also a opsonization factor.
Mm-hmm.
Okay.
Absolutely. Okay, so the complement receptor, CR1, complement receptor 1, it's also called CD35. It binds C3b and C4b. It promotes phagocytosis of C3b and C4b coated particles. So exactly as you said, complement can also be an opsonin. This complement receptor also can clear immune complexes from circulation.
So it's on phagocytes, macrophages.
Actually, you know what the largest complement receptor reservoir in the blood is? What cell actually is the largest reservoir of complement receptor?
Red blood cells?
Red blood cells, right. That's the main sponge that sucks up all these immune complexes, and then it's cleared in the spleen, strips them back off.
We're going to get to this in a second, but in regards to your question, Mark, on table 14.6, it has complement receptor 1. Complement receptor 1 is on macrophages, so all mononuclear phagocytes, neutrophils, BT cells, erythrocytes, eosinophils, follicular dendritic cells.
And actually, a deficiency of complement receptors on red blood cells is associated with increased activity of autoimmune diseases like lupus.
Okay. All right, I see. Okay.
All right. Next, complement receptor 2, which is also called CD21, which is a co-receptor in B cells, stimulates the humoral immune response. It also promotes trapping of antibody-antigen complexes in the germinal centers of lymph nodes. It binds C3d, C3dG, and IC3b, which are breakdown products of C3b. It is also the cell surface receptor for EBV, so this one obviously is very important to know.
So what's that CD21, CD19, CD18 thing, or CD81?
The co-receptors for the, basically, remember the B cell? We were talking about the B cell receptor. They've got your immunoglobulin, they've got CD19 and CD21 right next to it. All right, CR3, that's supposed to be CR4, not C4. are good ones to know. They're integrins. They're receptors for IC3B, which remember stands for inactivated C3b. It's a breakdown product of C3b. So CR3 is also known as MAC1 or CD11B, CD18. C4 is CD11C, CD18. So in what immunodeficiency do you lack complement receptor C3 and CR3 and CR4? LAD1. So I think that's just a tricky point to remember because we usually think of LAD1 as adhesion, but remember these are also complement receptors and it could be worded as such on board's test.
So complement receptors also recognize complementary proteins on endothelial cells, allowing them to adhere.
There's two. So we already talked about SINR1. They also mentioned a complement receptor of the immunoglobulin family, CRIG, which is on Kupffer cells in the liver, macrophages in the liver. It clears blood-borne pathogens. There is, did I put the wrong table on here? I think I did. This is here. Yeah, sorry about that. Okay, so this is supposed to be table 14.6, which shows the receptors, and it shows the structure, ligand, cell distribution, and function. It's on page 338 of Abbas. All right, so regulators of complement. So C1R and C1S, remember from the classical pathway, are inhibited by C1 inhibitor. So if you do not have inhibition of C1R and C1S, you have lots of C4 being cleaved. So if you think about hereditary angioedema, the screening test to look for is C4 level, and this is why. Remember in that beginning C1Q, C1R, C1S complex is cleaving C4 to generate that C3 convertase. You're using up all that C4. You're not inhibiting C1R and C1S because you don't have C1 inhibitor. So C4 is going to be low in active disease and not in active disease. And the patient is always going to be low. Okay. Now, if C3b is on mammalian cells, it is bound by proteins that competitively inhibit the formation of C3 convertase. These proteins include membrane cofactor protein, CR1, DAF, and factor H. So these are all competitively inhibit.
Are deficiencies of each of those described? Or
Yes.
Oh.
At least DAF, factor H, CR1, but we'll talk about that in a second. Okay, so this is figure 1413. It shows regulation of C1 activity by C1 inhibitor. So the C1Q binds to antigen complex antibodies, resulting in activation of C1R2S2. C1 inhibitor prevents C1R2S2 from becoming proteolytically active, so it actually removes them from the C1Q. Nice thing to have around in your body.
Yeah.
Figure 14.4 of same page, 340 of Abbas, shows inhibition of the formation of C3 convertases. So you have formation of C4b2b complex, or the classical pathway C3 convertase, and then this basically shows DAF, or complement receptor 2, MCP, displaces the C2b from the C4b. Here we have formation of C3b-BB, which is alternative pathway C3 convertase, and similarly, this is going to take off the BB to inhibit the complement pathway.
Just knocks it off.
Complement initiation.
So is that C3b, is it just connected to the surface of the cell, like this somehow?
Yes.
It looks like the two
I thought it was like
CB aren't. They're just connected to the C3b.
All right. Other regulators of complement include factor I, which degrades C3b. MAC formation is inhibited by CD59, and MAC insertion is inhibited by factor S. That is shown here on figure 1415. Shows factor I mediated cleavage of C3b on page 341. And I believe there's one more. Figure 14.6 shows regulation of formation of MAC. They get activation of the late components of complement, formation of MAC, and then C59 inhibits that poly C9. And then the S protein inhibits insertion of the C5 BC7. So negative regulators, S protein and CD59. Okay, so deficiencies in these can cause different things. Deficiency of DAS and CD59 cause paroxysmal nocturnal hemoglobinuria, and C1 inhibitor deficiency, like we mentioned, causes hereditary angioedema. I actually pulled out this old book that I like so much, and if Dr. Parslow is around in the scene, please update this book. It's from like 2001, I think. Medical immunology. You may be able to get it on Google for like $1, but for medically relevant immunology, it really has some fantastic things in
The
it.
Harriet Lane series, yeah, medical immunology.
Oh, Lane. I don't know. You may have to get a used copy, but I think you can still get them on Google for just pennies. The basic immunology I don't like as well as Abbas, but the medical immunology, clinical immunology is great. So one of the things that I printed off was from chapter 25, it's table 25.1, and it shows inherited complement and complement-related protein deficiency. So big things to remember. Of course, if you have late complement deficiency, you're going to be susceptible to Neisseria infections. Early complement deficiencies, like Dr. Portnoy mentioned earlier, you are susceptible to autoimmunity.
Okay. So if somebody comes in with Neisseria meningitis or Neisseria or gonococcal septic arthritis or something like that, do you recommend just measuring complement routinely in such a
Well, CH50.
total complement.
Total complement.
Not the individual components, because if total complement's normal, you're okay. But if it's absent and you repeat it and it's still absent, then you might want to enumerate the individual component. But do you recommend doing total complement in somebody with Neisseria meningitis or septic arthritis? Just routinely?
I don't know that I would do it on everybody. But on the correct clinical presentation, I think I would.
Yeah, because I've always thought that if you have Neisseria meningitis, total complement is so cheap in terms of the total treatment course, which is going to involve inpatient and ICU and all life-threatening and all of that stuff. You know, adding one additional test, because if it's abnormal, they'll be back, and if they come back for the second time, they're not going to be happy that you didn't measure it the first time.
Do you wait for them to get better before you check it? Or can you check it while they're sick?
Complement while they're sick? Why would it?
I'm just wondering if
it wouldn't really matter.
I mean, is the complement being consumed because of the
it's all being consumed because you're fighting all this infection.
Give you like it wouldn't be due to the
maybe because you're going to see them back for follow-up.
I mean, if you're going to see them back for follow-up. You know.
Yeah, so I suppose that would be the best time to do this.
I think that's why a lot of people order C3 and C4 with CH50, because if the C3 and C4 are low, it lets you know that the CH50 may be
low because of consumption as opposed to an absence of one of the components.
You're not measuring C3 or C4 to see if that's low. You know, you're checking the validity of the CH50 test.
Yeah, that makes good sense.
Would you?
Go ahead.
But would you also check it on anyone who came in with a gonorrhea infection?
If it's urethritis, probably not. But if it's septic arthritis, then why did it get from the urethra to the joints? I would ask why that happened, because that's an atypical type of infection. So then I probably would.
And then how would you support with them with prophylactic antibiotics, lifelong prophylactic antibiotics?
I suppose it's never come up because these are very rare conditions. But if it did, I would probably consider that. I would also be talking to my infectious disease colleagues, and we would design a treatment plan for it. Probably emphasize the vaccination program too for Neisseria. I mean, all college students should probably get that anyway. In terms of the C2 and C4 deficiency being associated with lupus, how do you explain an increased risk of autoimmunity with complement deficiency? Does anybody know why that would occur? Can you explain it? Please? See, my explanation has always been because of linkage disequilibrium. What do you know about C2 and C4 and factor B also? These are complement components that are encoded in the MHC, the major histocompatibility complex on chromosome 6. Abbas calls them the MHC class 3 antigens, but they're just coded right there. So they're very closely linked to the immune response genes that are also associated with development of autoimmune disease like lupus. So it turns out that if you have a deficiency in C2 and C4, then it's much harder for you to consume complement. So if you happen to have lupus, the lupus you have is going to be a much milder case because you're not going to have as much inflammation due to these deficiencies. And so these are actually protective immune deficiencies, allowing you to survive better if you have lupus, so you're more likely to have progeny who then carry that on. So it's not that C2 and C4 deficiency cause lupus, it's that they allow you to survive lupus, and because of the linkage disequilibrium, they tend to be inherited into your offspring. So you're more likely to have offspring who also then have lupus. So it's an interesting way of looking at it.
All right, we are out of time, but that's about it anyway. Let's see, this is, okay, so this is the table that Dr. Abbas actually gives. Table 14.7 on page 339 of the different regulators of complement. Okay. And that is about it. There is a bit more in this chapter that was just run out of time. But I think, let me just mention actually, one other thing they talk about is a secreted IgA in this poly-Ig receptor, which bounds dimeric IgA, is endocytosed, and then is proteolytically cleaved, and then you get your secreted IgA with your secretory piece, which is probably something important.
So complement helps to transport IgA into the lumen?
No, this is
a separate thing.
This is just humoral, yeah. Mucosal immunity, just a word about mucosal immunity.
Okay. Wow. Certainly a very complicated chapter, but I mean the C3b, BB, every time I look at it, it's a little clearer, but it's still always complicated.
Yeah. Actually, I did, I know we're out of time. I read something interesting recently in the in talking about food allergy.
Yes.
And there, I guess, there's a review in Nature recently that was really great when it talked about mucosal immunity, and it talked about how so when the mother, say, eats something like a peanut, then IgG can actually coat the peanut. The peanut IgG complex is secreted in breast milk and actually helps the neonate tolerate the peanut on their first exposure.
Right. I remember reading that, and mothers who don't do that are more likely to have allergic children. So it turns out that allergic mothers who breastfeed, their breast milk makes their children more likely to develop allergies. So breastfeeding may actually be harmful for your child if you happen to be an allergic mother. Not that we discourage breastfeeding, but just an interesting finding. All right, we're going to have to stop here. Thank you, Dr. Ciaccio, for this interesting discussion. It's always complicated to understand this, but certainly we'll make an effort. We're going to stop for about 2 minutes while we get prepared for our next presentation. I see our next presenter is here. So this has been Conferences on Lyme Allergy from Children's Mercy Hospitals and Clinics in Kansas City, Missouri. We'll be back in just about 2 minutes and we'll get started.
This has been an ACAAI production. To learn more about Conferences on Lyme Allergy or the American College of Allergy, Asthma, and Immunology, go to www.acaai.org. See you next time.